And what keeps the bug going in the circle has to be friction. For anything with uniform circular motion, the sum of the forces cannot cancel, Brad. You have to end up with a net force, a very special kind of net force called centripetal force. So ask yourself, for anything going in a circle, what's providing the centripetal force? Well, in this case, it's friction. In particular, the static friction. And then with friction, there's always a normal force. And in this case, the normal force happens to point up and must be equal to the force of gravity. So in this particular problem, the net force is a special kind of net force called centripetal force, and it's provided by static friction. These are not two separate forces, Brad. This is one force, friction, that also happens to be a net force and is a centripetal force. The normal force has to be equal to the force of gravity. To me, it looks a little smaller. Let me fix that. There we go.
Thank you.
The normal force must be equal to the force of gravity. These are two separate forces that are canceling each other to give a net force of 0. So these two expressions look similar, but they couldn't be more different. One force expressed two different ways. Two forces that happen to be equal. And we used those to find how far the bug got before he started to slip. And I can do that derivation for you again. You've seen it before. I can do it again for you later. But before I do that, I want to contrast this force diagram with something that looks deceptively similar, but is very, very different. Remember the problem from your homework involving the amusement park ride, where there was this cylindrical room, and people come in, stand on the floor, up against the wall, it starts spinning, and then the floor drops. In this case, the record was moving with some angular velocity, and here, this whole cylindrical room is moving with an angular velocity. What are the forces acting on this person? Well, of course there's a force of gravity, but the person sticks to the wall. They don't fall. Why not? Because of friction. The friction between the person and the wall is what keeps them from falling. And with any force of friction, there is, of course, perpendicular to that, a normal force. So in this situation, we have a very special kind of net force called centripetal force. But what provides it? Not friction. The wall does. The normal force does. One force, this time the normal force, that happens to be a net force, a special kind of net force called centripetal force. One force expressed two different ways. Friction and gravity, they cancel each other. The force of static friction is equal to the force of gravity in this case. Similar looking pictures, same three forces, both involving centripetal force and uniform circular motion. But the situations themselves and what creates the centripetal force are totally and completely different. So now, Brad, what would you like?
The bug one.
Do you want me to solve it for what that particular problem asked you to find?
Sure.
Because it asked you, how far does the bug get before he starts to slip? Okay? Well, from this, mass times centripetal acceleration equals coefficient of friction times normal force. Centripetal acceleration is tangential velocity squared over radius, and the normal force happens to be equal to the force of gravity, which is equal to mass times the acceleration of gravity. Are you okay, Brad, with the substitutions I've made so far?
Yeah.
Is everybody else okay too? At this point, you hopefully can see that the mass cancels. Now let's see here. We want to know how far the bug gets before he starts to slip. That means the radius of his path. Not the radius of the entire record, but the radius of the bug's circular path when he starts to slip. Because the farther out he gets from the center, the faster his tangential velocity, and the more force necessary to keep him going in a circle. but friction has a limit. So at some point, he gets so far out that he needs a force greater than what friction can provide, and that's when he slips. So we want not the radius of the whole record, but the radius of his path. We know the coefficient that was given to us. We know the acceleration of gravity. We want r, but we don't know the tangential velocity. Instead, we were given the angular velocity. But I know that tangential velocity is angular velocity times radius. Well, that's a problem. To get this other piece I need the thing that I'm trying to find. So how can I get what I need when what I need is what I'm trying to find ultimately? Don't panic in that situation. Substitute omega times r in for tangential velocity. Then notice that the squared and this r cancel. And we get that r is equal to mu g over omega squared. That's what the problem asked you to find. Just for fun, Brad, I'm going to solve this for the coefficient, which would be r omega squared over g. The only reason I'm doing that is I want to do the same thing over here, just to show you how different the final equation turns out to be if I solve for the coefficient. Again, we were given the coefficient, we weren't asked to find it, but let's say they gave us the r, let's say they told us the bug slipped 10 centimeters, what must the coefficient be, okay? I saw a hand up though.
Yeah, I was actually just going to ask for both of them. Well, actually, no, it was for the one on the right. Would we just be finding the normal force by taking gravity times the person's mass, or is there just a different kind of way of doing that? No?
No. See, did you say for this one?
Yeah.
Yeah, no. See, because the normal force is not equal to the force of gravity. That's the thing. We have so many problems on flat surfaces where the normal force ends up being equal to the force of gravity, but that doesn't have to be the case. Here, the normal force is totally dependent. It has nothing to do with gravity, I should say. It's dependent on just how fast the whole thing moves. The faster that room moves around, the greater the normal force you would feel. The more you would feel like you were being pressed into the wall, when in fact your body's trying to go in a straight line and the wall won't let it. So how do you get the normal force? Well, it's a function of how fast this room is spinning. You'd have to be given that. Let's derive an equation for the coefficient of friction in this case here. I know that the force of static friction is equal to the coefficient of friction times the normal force, and that's equal to the force of gravity. Well, the normal force is equal to centripetal force. So the normal force is equal to mass times centripetal acceleration. So I'll plug that in for the normal force. And the force of gravity is mass times the acceleration of gravity. Notice how the mass of the person cancels. That's nice. So we don't have to worry about how heavy a person does this ride. Every single person should experience the same sensation of being stuck to the wall, regardless of their mass. If I now solve for a coefficient, that would be g over a sub c. A sub c is vt squared over r. So the coefficient is g over vt squared over r. I don't like fractions within fractions, so that would be rg over vt squared. But then I know that vt is omega times r, so the coefficient would be rg all over omega squared r squared. Then this r cancels that squared, so the coefficient would be g over r omega squared. Isn't that interesting? Look at those two equations. They're exact inverses of each other. And it's because in the diagrams that initially look so similar, the normal force and friction are switched. It's an inverse relationship between the two. Here, for the bug, friction provides the centripetal force, and normal force cancels gravity. Here, friction cancels gravity, and the normal force provides the centripetal force.